This is section 1.4. We're going to talk about continuity and one-sided limits. This video is going to focus on continuity. So let's go ahead and get an informal definition of continuity. The informal definition says that a function is continuous if you can draw the graph without picking up your pencil. So that's the most common way that you will hear this defined. If you can draw the entire graph without having to pick up your pencil to make a hole or a jump or something like that, then we would say the graph is continuous. Of course, we're not going to keep it that simple. We're going to get a much more technical definition of continuity. But a function is not continuous, or you might say it has a discontinuity. That would be another language that we would want to use. At a point x equals c, if the graph is broken at that point by a hole, a jump, a gap, etc. So for example, this might be what a hole would look like. F of c just happens to be not defined at this point. In this case right here, the limit as x approaches c of f of x does not exist. It approaches a different value from either side. And in this case, the limit as x approaches c of f of x does exist. It's approaching whatever this y value is right here, but that's not equal to the function value at c. So this would be the hole, the jump, the gap, whatever you want to call those. That is the informal definition of continuity. And as you may have guessed, if we have an informal definition, we're also going to have a formal definition. So this is the formal definition of continuity at a point and on an open interval. A function f is continuous at a point c when these three conditions are met. F of c is defined, the limit is f of x, the limit of f of x as x approaches c exists, and that limit is equal to f of c. And we say it is continuous on an open interval a to b when it's continuous at every point in the interval. And you may have some functions where they're continuous at every point on the open interval, negative infinity to infinity. That's the entire real number line, and that would be everywhere continuous. So one thing that's very important to note is that in order for f to be continuous at a given point, all three of those conditions must be met. If any condition fails at c, f is not continuous at x equals c. Also, if a function f is defined on an interval I except possibly at c, and f is not continuous at c, then f is said to have a discontinuity at c. So if it's not continuous in a point, it has a discontinuity at that point. Now let's talk about the categories of discontinuity. There are two basic types of discontinuity, removable and non-removable. And we've already seen these in our images that we showed earlier, but we're going to look at those in a little bit more detail. So a discontinuity at c is called removable when f can be made continuous by appropriately defining or redefining f of c. So this could include factoring out a common factor from the numerator and the denominator of a function. This is similar to that dividing out technique that we talked about earlier. It could also be something like the rationalizing technique. If you can take algebra or just redefining a piecewise function and saying one small change makes this graph continuous at that point, then that's a removable discontinuity. So it would look like this. If you had a hole at that point, it would look like that. Or it may be a piecewise function where your function is just defined as saying, okay, it's in this curve everywhere except for c. And you can just say, okay, I'm only going to change that one point and make it continuous. So these are both removable discontinuities. So the limit, in both of these cases, the limit as x approaches c of f of x still exists, but it isn't necessarily equal to f of c. So that's what one of the things that defines or distinguishes a removable discontinuity. Now, a discontinuity at c is considered to be non-removable if you cannot make this change. So this usually involves a complete jump of the graph. So it might look something like this. So notice here that it would take much more than just one point changing in order to close that gap in the line or that break in the line. These are examples where the limit as x approaches c of f of x just flat out does not exist. If the limit doesn't exist, then you know it's going to be a non-removable discontinuity. Now, you'll have a lot of problems where you're asked to discuss the continuity of a function. And whenever you are asked to discuss the continuity of a function, what you want to do is you want to list all intervals. And remember, these are intervals of domain elements, so you should put them in interval notation, where the function is continuous, and the other thing that you should do is identify all removable and non-removable discontinuities and which type they are. So we're going to look at a couple of examples of discussing the continuity, and you can see what that looks like. So for example, I've got f of x equals 1 over x, and it's not necessary that you absolutely must graph each of these functions. I'm just going to put a graph up here so we can kind of see what we're talking about, and hopefully it'll make a little bit more sense to you. I'm just going to plug in a couple of points to get a graph. This one's pretty simple to graph. Of course, we know that it doesn't exist at 0. This would be negative 1/3, negative 1/2, negative 1, 1, 1/2, and 1/3. And if you keep plugging in more points, I think you'll see the pattern pretty clearly. We have a vertical asymptote at x equals 0 here. So it looks something like this. So keep this graph in mind, and you can look at it and you can see the informal definition and the formal definition. So we definitely have a discontinuity here. And you can see that we have a discontinuity at x equals 0, and because the line is actually jumping, it's not something that you can just piece back together by replacing one point. This is a non-removable discontinuity. If you were looking at the function, you could tell that it's non-removable because there's nothing you can do to cancel the x out. So we have a non-removable discontinuity at x equals 0. However, it is continuous everywhere else. So on this graph right here, you can see that you can draw this whole left side without picking up your pencil. So we're continuous on all of these points. We're also continuous on all of these points. So to put that in interval notation, we are continuous on the following: from negative infinity to 0. Notice these are open intervals. I'm not putting a bracket. And from 0 to infinity. One thing that's important is that you don't want to union the two of these intervals, because you're not continuous on the union. There is that point in the middle. It has to be just one single interval in order to be continuous on it. And just to do a little quick review of interval notation, if you have parentheses around your border points, your endpoints, this is an open interval. A and B are not included in this set, but every value between them is. So this is all x that are such that x is greater than A and less than B. If you have brackets, this is closed, and it's understood that the endpoints are included. So this is the same thing as having greater than or equal to symbols with those inequalities. So let's look at this example, and I'm going to take this from the kind of analytical approach first. I'm going to look at the f of x equals x squared minus 4 over x plus 2, and I know that I would have a problem at x equals negative 2. So because if I set x plus 2 equal to 0, I get that x would be equal to negative 2. So we know we've got a discontinuity at x equals 2. We just need negative 2. We just need to figure out what kind it is. This factors to be x minus 2 times x plus 2, which means that this cancels out. So because I can cancel out the factor that caused it, I know that this is a removable discontinuity. And there's no other possible problem, so we know that this one would be continuous everywhere else. So it's going to be continuous on the interval from negative infinity to negative 2 and the interval from negative 2 to infinity. Now if you wanted to graph this, you could see that as well, what it would look like. So we know that it doesn't exist at negative 2, doesn't exist there, but if you plug in some other points, you get what looks like the following. So we have negative 1, negative 3, 0, negative 2, 1, negative 1, 2, 0, and then it looks like it's just a straight line everywhere except where there would be a point at negative 2. It doesn't exist. So you can see the informal definition of the continuity in that graph if you try to sketch it out. Taking a look at this example, I have f of x equals x minus 3 divided by x squared minus 9. So in this case, I know I've got problems at x equals plus or minus 3. So I know I've got a discontinuity at x equals 3, and I've got a discontinuity at x equals negative 3. So I just have to figure out which kind each of those are. So if I factor out the bottom, I would have x minus 3 times x plus 3. So I can factor out that and cancel it. So I have 1 divided by x plus 3. Now, if you're looking at this graphically, because the x minus 3 cancels, that means you would have a hole in your graph at x equals 3, and you would have a vertical asymptote at x equals negative 3. Now, the vertical asymptote x equals negative 3 is going to be a non-removable discontinuity. The hole is going to be a removable discontinuity. So this is part of our answer. And the other part of it is that we are continuous on all of the other intervals. So that would be from negative infinity to negative 3, everything between those 2 points, and everything to the right of 3. So that's the other part of our answer. If you wanted a graph, you could plot some points, and your graph would look roughly like this. So you can see the removable discontinuity, the non-removable discontinuity, and all the sections where it is continuous. Now this special example is a piecewise function, and with piecewise functions, sometimes it's really just best to go ahead and get a graph of it. So we're going to plug in some points. I'm going to plug in points to the left of 0 and to the right of 0. So I'll do negative 2, negative 1, and 0. And this will go with that closed circle right here. So if I plug those in, I'd have 4 minus negative 2 is 6. 4 minus negative 1 is 5. 4 minus 0 is 4. So negative 2, 6, negative 1, 5, 0, 4. And that's a closed circle. So that goes up this way. And on the other side, I would have 0. We'll plot 0 again with the other graph, and that'll be open. 0, 1, and 2 will give us 4, 5, and 6. Now an open circle over a closed circle kind of fills each other in. And then I'll have 1, 5, and 2, 6. So it ends up filling in all of the dots. And in this case, there are no discontinuities. And this graph is continuous everywhere. So you could say that it's continuous on the interval from negative infinity to infinity if you have to list an interval. And that is basically what it means to discuss the continuity of a function.